Up to this point, we've done inferential methods where we only considered a single population parameter. We did inferential methods on the population proportion, and we did inferential methods on the population mean, both confidence intervals and hypothesis testing. What we're going to do now is jump to comparing parameters from two populations. So we're going to compare two population proportions, and we're going to compare two population means. So we are going to be comparing initially two population proportions. To get you into the groove on how this method works, I laid out a scenario for you. Here at Joliet Junior College, we actually have something called a math redesign program for our different developmental math courses. For intermediate algebra, we wanted to know whether students have a higher pass rate in this redesign course than they do in a traditional course. To help answer that question, during the spring of 2015, Laura Egner here at JJC taught a section of each model. In her math redesign program course, 19 out of the 24 students passed the class. In her traditional class, 14 out of 24 students passed. So what we wanted to know is, does that constitute evidence to suggest the MRP course is superior to the traditional course in terms of pass rates? So if you think about the way this study was designed, you can basically think of those 48 students, the 24 in the MRP and the 24 in the traditional, as our sample, right? Basically, we can think of them as randomly being assigned to one of the two courses. 24 went to the MRP and 24 went to the traditional. So in that respect, we can kind of think of this as a completely randomized design with two treatments, right? Well, really one treatment. You either get the MRP course or you get the traditional course. Follow? The variable of interest, the response variable in this study, is whether the student passes or not. So it's qualitative with two possible outcomes. You either pass or you don't. And because it's qualitative with two possible outcomes, it's reasonable to analyze this using proportions. So what we want to know is what proportion of students in the MRP program passed and what proportion in the traditional passed. P hat for the MRP is 0.792. That's 19 out of 24. P hat for the traditional is 0.583. That is 14 out of 24. So based on the sample data, it sure as heck looks like the MRP course is superior to the traditional. In fact, if we computed the difference in sample proportions, we would find a difference of 0.209. So we had a almost 21% higher pass rate in the MRP course than we did in the traditional. So based on the sample data, you'd say, wow, it seems like the MRP is a superior program. But what we really want to ask is that difference statistically significant under the assumption that the courses are not going to have different pass rates? So remember, the null hypothesis is always a statement of no change, no effect, no difference. Meaning the null hypothesis would be the proportion of students who pass in the MRP is the same as the proportion of students that pass in the traditional. All right, so again, that 0.209 seems significant. What we want to know is, could we get that type of a sample difference by pure chance? Put another way, we had 33 total students who passed. 19 in the MRP, 14 in the traditional, 33 altogether. Is it possible that those students would have passed regardless of which course they were in. And just by pure chance, 19 of those students that would have passed ended up in the MRP, and only 14 ended up in the traditional. And the treatment itself of the course delivery system had nothing to do with whether they passed or not. It's just pure chance that the 19 ended up in the MRP, and that's where that difference came from. Is it possible that that could happen? That's our ultimate question here. All right? So basically we have two possibilities. The MRP course is not effective at all, and the higher pass rate was simply due to chance that though we had more students that happened to show up into the MRP, but those students would have passed whether they were in the MRP or the traditional, didn't matter. Right? The other possibility is the MRP course is effective, and the reason we saw that higher pass rate in the MRP course is because the MRP course is an effective tool for increasing pass rates beyond that of traditional. That's what we have to figure out. All right, so again, the statement of no change, no effect, no difference is that the proportion of students who would pass in the MRP is equal to the proportion who would pass in the traditional. What we're looking to gather evidence to show is, in plain old English, is the traditional course less effective than the MRP? Put another way, is the MRP more effective in terms of pass rates than the traditional? And so we would structure that alternative hypothesis. I'll fix that. That should be an H sub 1. We structure the alternative hypothesis as the proportion in the MRP is greater than the proportion in the traditional. So we are going to figure out whether the observed differences are due to random error or if the differences are significance. When I say due to random error, it basically means the MRP course and the traditional do have the same pass rates, and it was just pure chance that we ended up with 19 in the MRP and only 14 in the traditional. To answer this question, what we're going to do is use something called a randomization model. A randomization model. I'm going to go into StatCrunch to show you how this model works. So basically in StatCrunch, what I've done is I've loaded in my raw data. I have two different courses in the data. I have the MRP course, and then down below I have the traditional course. For each student in the MRP course, I indicate whether they passed or did not pass. Pass, I have 19 passing. See that? And then the remaining students, the 5, did not pass. And then below that are my traditional students. And I'm going to have 14 that passed, and then I'm going to have 9 that did not pass. This is my actual observed results. What I'm going to do now is go to an applet, resampling, and I'm going to do what's called a randomization test for two proportions. I'm going to select from my outcome only those where the course equals MRP. And then I'm going to select from the outcome only those where the traditional, where the course equals traditional. And I'll label these traditional course. Here, a success is pass. So my first sample, I sample from the MRP. For the second sample, I sample from the traditional. I then click compute. Now what you notice over here under runs, there's my raw data. That's where I actually started from. And then it computes the proportion who passed in the MRP, 0.792, see it? And the proportion that passed in the traditional, 0.583. And you can see from the bar chart the difference in proportion of passing for our observed data. And then down here in this second row it says the proportion, how often are we going to see 0.208 or higher under the assumption the null is true. What I'm going to have the applet do is, remember I said the null is that, yeah, we had 19 in the MRP that passed and 14 in the traditional that passed, but is it possible that those 19 just ended up in the MRP by chance, and they would have passed regardless of which course they were enrolled in? And so this applet is going to take my 48 students and randomly assign them to a course, keeping the pass and not pass with that student. And by randomly assigning them to a course, I'm basically saying there is no difference between these two courses, and let's see how often I get 19 or more of the passers in that MRP class. So watch how this goes when I click one time. I click one time, it randomly assigns the course to the outcome, and then it computes this difference in proportions. Okay, so here is, so if I click 1, there you can see the raw data. When I randomly shuffled, I got 66.7% of the passers in the MRP, and I got 0.708 of the passers, 70.8% of the passers in the traditional. Let me do this one more time so you can see it. Again, randomly assign the course to the outcome and compute the difference in proportions. And I'm going to do this over and over and over again. I got these 33 students that passed. I have 15 that did not pass, and I'm going to randomly assign them to either the MRP or the traditional course. What that random assignment is doing is basically assuming the statement in the null is true, that whether you pass or not has nothing to do with which course you're in. And then the applet down here is going to record how often we observe results as extreme or more extreme than those we actually did observe. So now I'm going to do this 1,000 more times. You see that? And I could do it 1,000 more. And what you see down here, 0.1014, is the proportion of times we observed a difference of 0.208 or higher under the assumption the null is true. Meaning about 10% of the time you're going to have 19 or more passing in the MRP. There's another way to think about this to help you visualize what's going on. If I go to applets, simulation with an earn, what I can do is basically say, let's make green passing. So how many passers did I have? 33. And let's make red failing, and I had 15 failing. Correct? I'm going to draw 24 balls. And I'm going to count how often I got 19 or more passing. So if you think about what I'm doing here, I have in a pot 48 balls, 33 of which are my passing students, 15 of which are my non-passing students. I'm going to draw 24 balls and throw them into my MRP course. Give them the course and see how often I get 19 or more passing. So I'll do this a few times. When I click one run, I got 17 passing. See that? 17 green balls. Click one run again, watch. I got 19 passing. So that time I got the same result as I got when I actually did the experiment. If I do this 1,000 times and 1,000 times, see how these results are pretty close to each other. So the applet on the left and the applet on the right are testing the same thing. The one on the left, what's nice about it is it's literally counting how often did I observe 19 or more passing in my MRP course. About 10% of the time, if there's no difference in the courses. The applet on the right did the same thing. How often do I observe a sample difference of 0.208 or higher under the assumption that there is no difference in the courses? Would you be willing, here's the big question, would you be willing as, say, department chair of JJC or Laura Egner, coordinator of all developmental math, or the president of the college, would you be willing to change the entire developmental math sequence and curriculum based on these results? I'm going to say it this way. We saw 19 pass in the MRP and only 14 passed in the traditional. Got a sample difference of 0.208. It sounded like a lot, right? 5 extra students passed in our MRP course. That sounds like a lot. But you could get those types of results about 1 every 10 times, even if there is no difference between the two curriculums. In other words, you observe something that could easily happen by chance 1 out of every 10 times if there is no difference between the courses. So based on that, are you willing to change the entire curriculum of JJC's developmental math sequence? Probably not. So even though the sample data sound incredibly convincing, when it comes down to doing the statistical analysis, it's not as convincing. This method that we just showed you will always work. And in fact, we can continue with our little story here now. What if we increase the sample size? So Laura said, yeah, that 1 semester sounded great, but I want to keep trying this to see if I continue to get these types of results. In other words, the results were encouraging, but we need further study. So let's say we continue this, and now that trend continues. That passing trend continues. After 5 more semesters, we had 95 out of 120 in the MRP program pass, and 70 out of 120 traditional students passing. And so the sample difference proportions are the exact same. And so again, our null hypothesis here would be that the proportion in the MRP equals the proportion in the traditional, versus our alternative that the proportion in the MRP exceeds the proportion in the traditional. Each of these p hats is the same as it was before. So if I did 95 out of 120, what do I get? What was it, 0.792? Yeah. And if I do the p hat for the traditional, I get 70 out of 120, which is 0.583. See how they're the same sample proportions? The only thing that happened is my sample size went up 5-fold. If I go back to StatCrunch and I do my earn, how many passed altogether? 95 plus 70 is 165, right? And how many did not pass then? 50 over there and 25 over there is 75, right? So I'm going to be drawing 120 balls out of my earn. I want to know how often I observed at least 95 passing, because that's what I actually observed in my MRP course. So I'm just going to jump right to the chase. How often do I observe this? That type of result, how is it rare? Yeah. Super rare. There's the one time that I did it under the assumption that the courses are the same, have the same pass rates. This number over here, these proportions that you're seeing, those are p-values. Remember what a p-value is? The probability of observing a statistic as extreme or more extreme than the one you did observe under the assumption the null hypothesis is true. For this earn applet on the left, we conducted this experiment 7,000 different times, and we only observed a sample difference of whatever it was, right? We only observed 95 or more passing, maybe a better way to put it, in the MRP course, one of those 7,000 times. highly, highly unlikely to observe those types of results if there really is no difference in the way the two courses, the outcomes of the two courses. Right? I could also do that with the applet over here. What I can do is I can just use this from summary down here. See that? 95 out of 120 successes in my MRP, right? 70 out of 120 successes in my traditional. Click compute and just randomly assign over and over and over again. Pretty similar p-value. Now, what I want you to take note of, first and foremost, a couple things that came out of this. One, my pass rates remain the same when I had just 24 in each class versus 120 in each class. Pass rates remain the same. The big difference between the only 24 in each class versus the 120 in each class was only sample size. By increasing my sample size and maintaining those same pass rates, I now do have what you would consider to be statistically significant evidence. If this truly was the evidence that we were getting here at JJC, it would be a no-brainer to switch to the MRP course, because you only observe those types of results 1 out of 7,000 times, right? If there really was no difference in the courses. So clearly there must be a difference in the courses. And the MRP is a superior model for increasing pass rates. So one moral of the story is this. Watch out for studies where you see small sample sizes that claim they're not statistically significant results. It is incredibly difficult to find sample data that would lend itself to statistically significant results when you have small sample sizes. The evidence has to be overwhelming. The flip side of that, of course, is watch out for studies that have super large sample sizes, because they virtually all the time are statistically significant, because super large sample sizes lowers your standard error. So there's a sweet spot in statistical studies for sample size. That's why your polling is usually in the 1,000 range, 800 to 1,000. It's a sweet spot for getting a sense for the variability in the data, but at the same time not causing your standard error to be so small that everything is statistically significant. So that's one lesson. A second thing to look at. What do you notice in both of these distribution shapes? They're both bell-shaped. You see that? Suggesting that perhaps rather than doing all this randomization stuff, I could just simply use a
normal model.
Normal model. Very nice. If you look over here, where's the center of the distribution at? 0. If we assume the proportion in the traditional equals the proportion in the MRP, then the difference in those proportions would be expected to be 0, right? So if we think the proportion in the traditional equals the proportion in the MRP, we would expect their differences to be 0. And look at, they are on my randomization model here. So the bottom line is this is suggesting to us that perhaps we could use a normal model to do this analysis as well. And we can, provided, of course, certain conditions are satisfied. And here is the sampling distribution for the difference between two proportions when you have an independent sample. You're going to take a simple random sample size n1 from the first population. X1 of the individuals have some characteristics, such as passing a class. And a simple random sample of n2 is independently taken from a different population where x2 of the individuals have a specified characteristic, again, such as passing a class. The sampling distribution of p hat 1 minus p hat 2, where p hat 1 is the sample proportion of successes in your first sample, p hat 2 is your sample proportion of successes in your second sample, is approximately normal, where the mean of that difference is P1 minus P2. But again, because we assume the proportions are equal in the null, P1 minus P2 is going to equal 0. The standard deviation is going to be that ugly formula right there. It's going to be normal provided n times p hat 1, 1 minus p hat 1 is at least 10. That's our normal condition for the distribution of p hat to be approximately normal. And then n2, p hat 2, 1 minus p hat 2 is also at least 10. And then lastly, each sample size can be no more than 5% of the population size. So notice your model conditions are pretty much the same as they were for a single proportion, right? Our mean and standard error are a little bit different. If we standardized the model, we would get this. Remember, to standardize, it's always statistic minus parameter over standard error, right? P hat 1 minus p hat 2 is your statistic. P1 minus P2 is your parameter, which for our cases is always going to equal 0 because we assume P1 equals P2 in the null hypothesis. And then there's your standard error down there. That has an approximate standard normal distribution. And remember, we use Z for standard normal. It means the distribution is approximately normal with mean 0 and standard deviation 1. This is just notation for a normal distribution. You put the mean there and the standard deviation there. Now, in the null hypothesis, remember we're assuming P1 equals P2. And when we do hypothesis testing, we approach our model under the assumption the null is true. Well, if P1 equals P2, then P hat 1 and P hat 2 should both be coming from the same population. And if they're both coming from the same population, both P hat 1 and P hat 2 should be proxies for the overall, the equivalent population proportion. So if we're assuming these are equal, it makes sense to merge the results from sample 1 with the results from sample 2. This is what the pooled estimate is called. So you just add your successes in each sample and you add the number of trials in each sample. And if we do that, this becomes the test statistic, where P hat is your pooled estimate. We kind of factored it out. Right? If you look here, if we say this and this are the same thing, we can factor it out. Okay? So there's your test statistic, and that should have underscores for division. To do hypothesis tests regarding the difference between two population proportions, this is the process that we follow. First and foremost, make sure the normal model applies. For the normal model to apply, the data have to be obtained independently using simple random sampling or are the result of a randomized experiment. The randomized experiment is going to be a completely randomized experiment with two levels of your treatment. Like in our MRP and traditional, we had two levels. You either went to the MRP or you went to the traditional. If you have 3 or more levels, it's a completely different model. Stay tuned. Right? So for right now, your explanatory variable is going to have 2 levels. There's your normality condition right there, and here's your independence condition. This is the process that we follow. It's the same 5 steps that we've had in Chapter 10. First and foremost, determine your null and alternative hypothesis. You're going to either have a left-tailed, a right-tailed, or a two-tailed hypothesis test. Notice in all 3 of these, we assume the population proportions are equal because, again, the null is always a statement of no change, no effect, no difference. Second, decide on a level of significance alpha. Step 3, if you're doing the p-value by hand, you have to compute the test statistic using this model right here. Use a table to find the value of the p-value. Remember, the p-value is just the area under the curve corresponding to your test statistic. We will do this. Step 4, if p-value is less than the level of significance, we reject the null hypothesis. Remember, if the p is low, the null must go. And then lastly, you want to state your conclusion. So, we are going to do all that by hand using the math redesign program, and then we'll show you how to do it using technology. Ready? So, let's see if we can get the same types of results that we got from our randomization model earlier. Remember, we got a really low p-value, like 0.0001 or something like that, right? Okay. So, in the math redesign program, our null hypothesis is that the proportion in the MRP equals the proportion in the traditional versus the alternative, that the proportion in the MRP exceeds the proportion in the traditional. We want to know if the evidence tells us that the MRP course is a superior model. In the MRP, p hat is what? 95 out of 120, which we got 0.792, correct? In the traditional, we had 70 out of 120 pass, and that was 0.5 what? 583. Okay. This data, we can think of it as being a completely randomized design where we pretended we took 240 students and randomly assigned them to one of two courses, either the MRP or the traditional. Now, there's some flaws in that model design, in that designed experiment. I mean, we did hold a few variables constant, same semester, both in spring of 2015, same instructor, so the variability associated with instructor or semester is gone. We've eliminated that. They can't be taught at the same time, so time of day, if that is a factor that plays a role in whether one passes a course or not, that would end up being a confounding variable for us because we can't do anything about that. Laura can't be in the same class at the same time, right? But we tried to do as much as we could to make this as well-designed an experiment as possible. All right, so our first requirement of independent sampling is satisfied. We need n times p hat for the MRP times 1 minus p hat for the MRP to be at least 10. So if we go to our calculator, here's my calculator, n was 120, right? Times, what did we say, 0.783? 792 times 1 minus 0.792. We're getting almost 20, so we're good on that one. For the traditional, we need the same thing. So n times 0.583 times 1 minus 0.583, 29.2. So in both cases, our normality model is, or requirement is satisfied. And then last but not least, we need our independence requirement satisfied. Basically there, we have 120 students, right? There's thousands upon thousands of students that have taken this course, right, during our history, and so our sample size is definitely small relative to the size of our population. And so our independence requirement is satisfied. So let's say we're just going to use a 0.05 level of significance. Now step 3, we have to come up with our our normal model. The mean for the distribution of p hat MRP minus p hat traditional is going to be 0, because again we're assuming that the two proportions are equal to each other, therefore their difference is going to be 0. The standard error is a little bit trickier, and that is the square root of p hat 1 minus p hat times 1 over n MRP plus 1 over n traditional. Remember, p hat is your pooled estimate, so I have to pool the estimates. So my p hat pooled is going to be 95 plus, how many passed the traditional? 70, right? Divided by 120 in the MRP plus 120 in the traditional. So it's 165 over 240. What does that work out to rounded to 3 decimal places?
0.688.
Okay, 0.688. So I use that over here. 0.688. 1 minus 0.688. And then over here, 1 over 120 for my MRP, 1 over 120 for my traditional. So I use my calculator. Square root 0.688, 1 minus 0.688, like that. And then square root 1 divided by 120 plus 1 divided by 120, like so. Hit enter, I get 0.0598. So this is 0.0598. So my test statistic is the difference that I observed. What was this? 0.792 minus 0.583. Those are my two stats. Minus 0, because I'm assuming the difference is going to be 0. And then divided by 0.0598, my standard error. Go back to my calculator. 0.792 minus 0.583 divided by, to avoid rounding error, I'm just going to use that whole decimal there. 3.49. You see that? 3.49. Now I can do this one of two ways. Here's my actual model and difference in sample proportions. And I observed a sample difference of whatever this is, 0.792 minus 0.583. What is that difference? So this area right here is my p-value. Or if I want to just use the standard normal model, these are z values. There's 3.49. That also is my p-value. Because it's a right-tailed test, my p-value is the area under the normal curve to the right of my sample statistic or my test statistic. So if I go back to your buddy and I open StatCrunch, I go Stat, Calculators, Normal. The mean is 0. The standard deviation, what did I say? 0.0583. So, no, I said 0.0598. 0.0598. And you said the sample difference was 0.209, was it? Click compute, and there's my p-value, 0.0002. That's without standardizing. There, or if you want to use the standard normal model, that mean is 0, that standard deviation is 1, and we want to know the area to the right of 3.49. That was our test statistic. Same thing. 0.0002. Compare these to what we got from our simulation. Let me open that up. We got 0.0003 from one randomization. We got 0.0001 from another one. And we got 0.0002 from our normal model. So all three are essentially telling you the same thing. The chances of observing a sample difference of 0.208 or higher, assuming the two courses have the same pass rates, is very, very low. Because my p-value is so low, I take this as evidence against the statement in the null and reject the null hypothesis. Because I'm rejecting the null hypothesis, we're going to conclude the sample evidence does suggest that the MRP course has a significantly higher pass rate than the traditional course. And for that reason, we would recommend to the JJC Math Department that they should make this change. Now, for you folks, if you want to just go right to StatCrunch, we can do that. So to do this directly in StatCrunch, you still would have to check your model requirements, right? That the data is independent samples or comes from a completely randomized design with 2 levels of treatment. The normality condition would have to be satisfied and the independence requirement has to be satisfied. You structure your null and alternative hypothesis. You would then go to stat, proportion stats, to sample. And you can either do with data or with summary. Right? For our MRP, we have summarized data, 95 out of 120, 70 out of 120. Click that. For sample 1, our MRP had 95 out of 120 successes. For sample 2, our traditional had 70 out of 120 successes. The null is that the difference in proportions equals 0. We write it that way because we're assuming the two proportions equal each other, so their difference is going to be 0. And this happens to be a right-tailed test where proportion 1 is greater than proportion 2. If proportion 1 is greater than proportion 2, we would expect proportion 1 minus proportion 2 to be greater than 0. You then click compute, and voila, there's your p-value. See it? 0.0002, the same p-value we got when we went the long route using the normal model. So the only reason I showed you that normal model approach was to convince you that when you'd go direct to StatCrunch and use the 2 proportion test, it's computing the area under the curve to the right of your test statistic. Right? So once again, this p is very, very low, suggesting strong evidence against the statement in the null, and therefore we reject the statement in the null and conclude there is significant evidence to suggest the MRP course has a higher pass rate than the traditional.